good. All right. Thanks, Antonio. It's a pleasure to welcome Marika Taylor. We'll talk about entanglement and holography. Marika received her PhD from DAMP in Cambridge, and since then, after that, held research positions in Cambridge, Utrecht, and Amsterdam. Stanford, Amsterdam. Yes. She's now a professor at University of Southampton.
Thank you very much. So this is indeed to talk about entanglement and holography, and it's not assuming that you know very much about either of those two subjects. Hopefully I'll be able to explain it as I go along. So you may have noticed, however, that on the archive you're seeing the word entanglement and certainly holography increasingly frequently. And it's because there is a lot of interest at the moment in new connections between quantum entanglement, which many people use in the fields of quantum information, quantum computing, condensed matter, connections between this and people exploring fundamental properties in quantum field theory, in particular properties as you do renormalisation group flow, and people interested in holography for questions of black holes and quantum gravity. And the talk today is really going to be from the perspective of a quantum field theorist, which is, I think, the thing that unites us. Why we might be interested in quantum entanglement and how we might actually use this in quantum field theory and as a particle physicist. So as I said, I'm going to start with an introduction to what I mean by entanglement, and in particular, I'm going to talk about entanglement entropy. So we're going to start with an example that could come from a quantum mechanics course, really. So we have some quantum system, and we have a density matrix of that quantum system. And it might be a reduced density matrix in the sense that we took a system and we traced out particular degrees of freedom. So the basic definition of the entanglement entropy is simply the von Neumann entropy. Von Neumann was mentioned earlier on today. Von Neumann entropy associated with this density matrix. So we calculate the entanglement entropy as minus trace of rho log rho. Now, typically, and for the purposes of this talk, what I'm going to be interested in doing is considering a system where I can take a Hilbert space and I divide the Hilbert space into two pieces, so a bipartite partition of Hilbert space. So my complete Hilbert space can be considered as the product of two Hilbert spaces, HA and HB, and my reduced density matrix is then given by specifying the density matrix of the whole system, which is rho. I trace over the degrees of freedom in the part HB in this part of the Hilbert space, and that gives me the reduced density matrix rho A, and then I calculate the entanglement entropy using this formula. And one can show, it's a straightforward exercise that you can look up in a quantum mechanics book, that if your starting density matrix over the whole space, Hilbert space, is actually a pure one, then if you actually just interchange the roles of A and B, so you trace out B and you compute the entanglement entropy associated with rho A, or you trace out the degrees of freedom A and then compute the entanglement entropy of rho B, you get the same answer. So this is a diagnostic actually of having a pure system. So let's do a very simple example of this, which will build up to what people try to do in condensed matter physics. So a two-spin system. So we've got two spins. Each spin can be in an up or down state. And following a little bit the notation that a quantum information, quantum computing guy would use, I'm actually going to denote the state of the two spin states up and down as 0 and 1. And now I've got two spins, so each of the spins can be in the positions up and down with 0 and 1. And so, just to condense the notation here, this means that the first spin is in state 0, the second spin is in state 0, the first spin is in state 1, the second spin is in state 1. And again, as we were discussing in an advanced quantum mechanics course, if you write down this state for the whole system, this is a pure state. Okay. Now, for such a pure state, you can form the density matrix by the standard relation between the wave function, by this product. And now we can implement what I described on the previous slide. I can trace out over some of the degrees of freedom In particular, in this case, I've got a Hilbert space, which is basically the Hilbert space of two spins. So I can just trace out over one of the spins. So here, if I trace out over the second spin, then I can compute the reduced density matrix, and you can believe me, you can just go away and do the calculation. This is the reduced density matrix that you actually get. And you plug it into the formula on the previous slide, and you find that the entanglement entropy that you get is log 2. And if you repeated this, you can see that the whole system actually is symmetric between the first and the second spin. You would indeed, if you traced out the first spin, and computed the entanglement entropy of SB, you would get exactly the same answer, which is log 2. Okay, so this is a sort of, just a flavour of what you're calculating and how you're calculating with entanglement entropy.
And it's called entanglement entropy in a sense because psi is a state you would call entangled.
Okay, so I'm going to give you, on the next slide, I'm going to give you a very, in a sense, explain to you why I gave you this little example to actually explain to you what entanglement entropy might actually mean. Okay, so indeed, entanglement entropy counts the number of entangled bits between systems A and B. So in my example on my previous slide, I had two spins, and the two spins were entangled with each other. But a really very useful way to think about entanglement entropy for much of what we're going to be doing here is an equivalent definition, which is that if you exponentiate S, the entanglement entropy, that's the minimal number of auxiliary states you need to purify your density matrix. Okay, so now if I go back to my thing here, so if I exponentiate SA, I get 2. And so what we're saying is by tracing out over the second spin, well, if we added back 2 auxiliary states, 2 more states, we could then purify the system. And so this is basically a measure of the number of extra states that you need to have for the system to be pure, right? And so, to have no entanglement. Okay, so in a simple quantum mechanical system like this, it's obviously quite straightforward to compute entanglement entropy. If you go to nice textbooks like the famous Nielsen-Trang book on quantum information, the early chapters, they'll go through many examples of this, and you can actually, think about entanglement entropy and what it means and how to calculate it. Now, people doing quantum information theory, quantum computing, often use other measures of entanglement. So, this is one of the basic things they want to do. They're thinking about building quantum computing systems. They want to sort of see, how can they maximize the entanglement? How can they control that entanglement? So they might be interested in dividing a system not into 2, as I've just been doing, but they might want to divide it into 3, and then ask about how the 3 parts of the systems are entangled between each other, and they've got measures of that too. But as you go through, a lot of their literature, you find that entanglement entropy for them is one of their favorite measures because it's a very robust measure. I could give you all the formal properties, but it behaves very nicely under unitary transformations, under many types of local transformations, and in particular, it's additive. So if you take a direct product of 2 density matrices, then the entanglement entropy actually just adds. And that's not actually true of many of the other measures of entanglement. So it's a particularly nice measure. Now, this measure is used quite a lot by people working in condensed matter physics, and people working in quantum computing, but also people working in condensed matter physics. And typically, the kind of partitioning of the Hilbert space that they will be interested in corresponds really to partitioning space itself. So a condensed matter physicist might be interested in a discrete system of spins. Now, of course, the case I just discussed, which was 2 spins, was just a very special case of this. This is, showing you more spins. And here, the division that they would do is just to basically cut that spin chain into 2 and say, we'll trace out those spins and we'll keep those spins. And now that's a case of where we have a discrete system. If we think about this in the context of a continuum system, quantum field theory, again, a natural thing to do is to consider this. This is the spatial region of the quantum field theory. I'm suppressing time here. And so we could think about doing partitioning the Hilbert space according to a partitioning of space. So again, A is, you know, A is some region of space, and B is some part of, you know, some part of the spatial region, and we trace out the degrees of freedom associated with that region. Okay, now there's a lot of literature on calculating entanglement entropy for the first case that I show here. So this is a case of a one-dimensional spin chain, but you know, which is one of the best understood cases. But you know, there's a lot of literature on entanglement entropy computation in discrete system. Why do people like calculating it for spin chains? It's because spin chains have interoperability, and that helps you to actually do the computation. And another reason that people like calculating entanglement entropy is because it's been understood for some years now, and in particular I would say over the last 10 years by John Cardy and his collaborators, that entanglement entropy is a really good way to capture the physical behavior of the system. So in particular, we've got some discrete system, and we ask for the lowest energy state of the system, the ground state of the system. Now, if that ground state is one in which we have a gap to the nearest excitation, then what they you know, showed on very general grounds is that the entanglement entropy in that ground state scales as the area of the boundary between the spatial regions A and B. And the example I show here, this is sort of, because it's one-dimensional, the area is of course trivial, it's just counting a sort of number of points in the boundary. As we go up in dimensions, you know, if you think about having a lattice, a two-dimensional lattice of spin change, you'll be basically counting the number of spins which are on the boundary of the region A. And there's a, you know, there's very, you can prove this, but there's a very nice intuitive way to understand why this is the case. So if you're in a ground state in a gap system, correlations fall off exponentially. So correlation functions fall off exponentially. And so the only non-trivial entanglement that you're actually going to have is between spin pairs which are actually at the boundary. So, you know, entanglement between pairs which are not near the boundary, that's going to be suppressed exponentially, and that's not going to be contributing to the entanglement entropy. So that's where you understand this. Now, so if you have a system which has got a mass gap, this is how entanglement entropy behaves. Now, if we're in a conformal field theory or quantum critical theory, there's also a very characteristic behavior of the entanglement entropy in the ground state of that conformal field theory. And this was something which was shown by Frank Wilczek and his collaborators about 20 years ago. So one plus one dimensional theory, two-dimensional CFT in particle physics language. What they showed is that the entanglement entropy in the ground state of such a theory, so now it's not behaving in terms of the area of the boundary of the entangling region, but instead is actually going logarithmically with the width of the entangling region. So if again I go back to my picture, so if I suppose that my region A had some finite width, here I've shown it as semi-infinite, suppose it had some width. What they showed is that in a CFT, the entanglement entropy scales with the log of this width. And again, if you want to sort of think of intuitively why that is, you know that in a CFT, the correlation functions don't fall off exponentially, they fall off with power laws, and that's essentially the origin of that log. And the coefficient here, C, is the central charge of the two-dimensional conformal field theory, so the famous central charge. The log has to be dimensionless, so there must be some parameter in here, and the parameter that shows up is the lattice spacing in the underlying discrete system. So here I'm still talking about some discrete systems which are approximated by a CFT description. So, you know, the entanglement entropy scales as the log of the width of the entanglement region in units of the lattice spacing. Okay. So you're doing, suppose you're a condensed matter physicist, you're solving your discrete system via numerical methods, via integrability methods. You come up with this answer for the entanglement entropy for your ground state, and you say, aha, it's got a description in terms of a CFT. Effectively, the low energy behavior is a CFT. You come up with this behavior and say, well, actually, the theory is gapped. And that's essentially, people like to use this as a diagnostic of what is the behavior of the theory in the infrared. Okay, now, let's think about more general dimensions. So that was a result specific to a two-dimensional conformal field theory. If we're in a conformal field theory in more general dimensions, so here I've shown something, so this would be two spatial dimensions, and I'm suppressing time in this picture, so this is a 2 + 1 dimensional quantum field theory. So a two-dimensional conformal field theory, it has, again, these log terms, which are scaling basically as the log of the width of this region. And then it's got terms which are scaling as the area of the boundary of this region as well. Okay, so so this is written rather abstractly in general dimensions. So you get terms which scale as the area of this boundary, and then you get terms which scale as logarithmically with the width of this region. And again, the coefficient that shows up here has some relation to known coefficients in conformal field theories. So there's a trace anomaly in the stress tensor, and that coefficient is related to the trace anomaly. Okay. So this is, this you can argue again with general features. So again, if you solve your, you have some discrete system, you solve it by your numerical methods, you solve it from integrability methods, you come up with this kind of behavior for the entanglement entropy in the ground state. You say, aha, well, the underlying theory at low energies describing this is a conformal field theory. Okay, so this is why people use entanglement entropy. So computing entanglement entropy is related to efficiently working out what the ground state is, in a way I'm not going to explain here, but they like to do that. And as I've been sort of arguing, it can be used to characterize the different phases. So to understand what is the low energy behavior of the theory, is it a conformal field theory, is it a gap theory, is it something like that? And people also talk, they also kind of start to explore whether entanglement entropy could be something that is actually directly measurable in cold atom systems. So that's the reasons that they like to use this. Now, let's move to a quantum field theorist perspective. So now I'm not specifically insisting that I'm in a conformal theory. I'm thinking again of a quantum field theory shown here as two spatial dimensions. I take some region A and some region B. I'm tracing out the degrees of freedom in region B and computing the entanglement entropy associated with the density matrix of that region A. So you can work out on very rather general grounds that the entanglement entropy has a number of terms. So it has terms which scale with the area of the boundary of the entangling region. That's this term here. It might have some other terms which scale a slightly different way with the width of this region. It could have terms which scale logarithmically with the width of this region, and it could have some finite terms. So here the L that appears in this formula is always some kind of characteristic scale of this region here. Often you might compute this for something which is in any case spherically symmetric. So you could just replace these things with just the volumes of the region. Coefficients which are C, they're all dimensionless. So I should have said before, the entanglement entropy is a dimensionless quantity. So these things are dimensionless. And so there's a quantity, there's a quantity here that appears, epsilon, which must be a cutoff in the system. Okay, so epsilon is a small position space cutoff, so it's inversely related to an energy or momentum UV cutoff. So usually when we do quantum field theory, we use an energy momentum cutoff, so that would be my lambda. That's a large thing. Here epsilon, which is small, is a position space cutoff. So it's some UV cutoff. Okay, and again, I'm not going to go through the details, but you can argue on rather general terms, using the behavior of correlation functions and so on, that's what you're going to get when you try and calculate this entanglement entropy in a quantum field theory. Okay, now there are a lot of conceptual puzzles about this expression, and some of these conceptual puzzles are what I'm going to be trying to resolve today. First of all, I started with a very simple example in quantum mechanics, but it's clear that the actual expression I wrote down is going to be really hard to calculate outside a theory which is either free or integrable. Okay, because I had to compute, trace of rho log rho. Well, you don't usually calculate, a density matrix when you're doing quantum field theory, and computing the logarithm of a density matrix is even harder to do. Okay, so this is something that's, a pretty hard thing to calculate. There's a little bit of a cunning trick that people do to calculate this. So again, calculating the log of a matrix is particularly nasty. So what can we do? Well, we can play a bit of a trick, because if you take this expression and you take the limit n goes to 1, you just formally manipulate this expression, you will actually convince yourself that this is actually the rho log rho expression that we had before. So I mean, you just differentiate, just expand this near n equals 1, and you'll convince yourself that that's the case. So people in practice, what they try to do is calculate trace of rho to the n, where n is an integer, and extrapolate it down to n equals 1. And this thing, it's calculated so often it's got a name, it's called the Remy entropies. Okay. Now you can immediately complain here that, taking this limit, if we were teaching a math class, we'd be a bit worried, right? Because I'm going to calculate this, is it analytic as n goes to 1? Should I worry about that? And that's definitely something to worry about, and people have worried about it, but it's not going to play a role in this talk. Now, everyone here who works with gauge theories could also worry about trying to calculate this expression in a gauge theory. So I'm trying to, if my quantum field theory was a gauge theory, and I say, okay, I'm going to sort of split into regions A and B, and I'm going to trace out the degrees of freedom in region B, you can say, well, isn't that going to be very dependent on how I deal with my gauge fixing? Yeah, I mean, isn't that going to be problematic? And there's a more fancy way of saying this, which is that really everything I did relied on the fact that the Hilbert space factorizes, and that's a problematic issue in gauge theories. Okay, and that again is not going to be the subject of today's talk, but that's really a big conceptual issue. Now, the issue I am going to focus on in today's talk is the fact that the expression I've written down is manifestly UV divergent, ultraviolet divergent. So if you go back to my expression here, without looking at the details of it, I said that sitting in this expression, the generic structure of my entanglement entropy, it involves, I implicitly had to introduce an ultraviolet regulator, and it sits everywhere in this expression. And everything you usually calculate in quantum field theory, you don't have a regulator sitting in your expression. You go and actually, we calculate a scattering amplitude, a correlation function, whatever we're trying to calculate for whatever question we're asking. We usually don't deal with things which have regulators. So, in some sense, it's even, well, not worse, but I already made a choice of the type of regulation in the expression I wrote down in previous slides. Because if I chose to use zeta function techniques to calculate, or if I tried to use dimensional regularization, I actually wouldn't have got those power law divergences. They wouldn't have actually showed up at all. Okay. The logarithmic coefficients do show up in whichever scheme you're using, so sometimes people call them universal. But the power law divergences don't show up if you use zeta function dimensional regularization techniques. And of course, if you actually want to do calculations in quantum field theory, most of the time you will use something convenient like dimensional regularization, right? However, so you say, you can say, why did I write down these terms? So the way this literature really started was people were interested in condensed matter physics. So condensed matter physicists use quantum field theory as a tool to describe underlying discrete systems. They have really a physical cutoff in their systems. And so they use quantum field theory as a tool, but then they want to compare it back to their discrete system results. And, so they wanted, in that context, these things here, as I tried to explain before, the epsilons are really the physical cutoff of the system, the physical separation of the atoms in the system, or the spin chain. And so they wanted these terms because they have some meaning. But from, a theoretical physicist standpoint, this is really not very satisfactory, right? Because we don't like the fact that we have to use a particular type of regularization scheme to actually compare things with. Okay. So this is the issue I'm going to be talking about today. I'm going to really resolve this issue. I should say I'm not really going to be able to resolve this issue here. I'll come back to that at the end, but I will resolve this issue. And to do that, I'm going to learn some lessons from holography. Okay, now, from the purpose of the talk, we don't need to know very much about holography. We just need to know the basic sort of picture, which is that a class of quantum field theories in d dimensions can be captured by gravity in one extra dimension. So the most famous example of this is that conformal field theories in d dimensions are captured by gravity in anti-de Sitter space in d+1 dimensions. Not all conformal field theories, I should say, there are restrictions, but a huge class of conformal field theories are captured by gravitational physics in anti-de Sitter. And this is the case that's been known for 20 years now, or almost 20 years, but by now we can go well beyond conformal field theories, so we can do holographic realizations of explicitly broken symmetry, spontaneously broken symmetry, confinement, and so on. So I wouldn't say that models of ADS, ADS models for QCD, in my opinion, are not particularly successful because they don't get the essential physics. But we nonetheless have examples of really, theories which have, say, confinement, things which have spontaneously broken symmetry, and so on. Okay, so that's the first feature we know. Now, the second feature is the following. So in the picture I'm showing on the left-hand side, this is a sort of a cartoon of holography. So the shaded region here is meant to be the quantum field theory. And then the quantum field theory is captured by geometry, gravity in one extra dimension. Okay. So we've got some sort of complicated sort of space and gravity in that space. Okay. Now, the ultraviolet physics of the quantum field theory, so small distance scales in the quantum field theory, are captured by what happens in the boundary. So we take a small scale, a small region in the quantum field theory. It's really only sensitive to things which happen close to this, near the boundary. And if you want an intuitive explanation of that, that's about, causality, really. We can sort of think about things which could causally affect this little dot here. It clearly can't be affected by something happening way over here. Okay. Whereas if you're interested in things happening on bigger scales, infrared physics in the quantum field theory, that's going to be much more sensitive to what happens in the deep interior. And so here, we're interested in physics on a bigger scale in the boundary, the quantum field theory. It can be sensitive to physics right down deep in the interior. Okay. Final thing we need to know about holography. So you get some things for free in life and some things are not for free. So in holography, in the gravity description of the quantum field theory, there are some things that you can compute rather easily. Now, they're not the things that we would necessarily want to compute and learn to compute in a quantum field theory class. So the things which actually are computable rather easily are the partition function of the quantum field theory, and then correlation functions of gauge invariant operators. Yeah, so usually in quantum field theory, the first thing you calculate is scattering amplitudes. That's not very easy to calculate in holography. It's very rare in a quantum field theory course that we talk about computing correlation functions of gauge invariant operators. So I have in mind things like trace of f squared, composite operators. That's a hard thing to do in quantum field theory because renormalization of composite operators is tough. That comes in a sense for free in holography. That's something that's easy to calculate. Yeah, so things which you usually wouldn't be able to calculate in quantum field theory do come out quite nicely. Okay. So I said to you before that because the entanglement entropy wants you to compute a density matrix, which in turn is really relying on you being able to calculate the partition function, this is a pretty hard thing to calculate. Okay, in a anything but a free or highly strongly integral quantum field theory. But in holography, we can calculate partition functions, and thus it's perhaps not surprising that we have a remarkably simple recipe for calculating the entanglement entropy. And this was realized by Ryu and Takeyanagi in 2006, so a bit over 10 years ago now. So this is the same picture as before. I apologise, sometimes my pictures sort of flip from being horizontal to being vertical. So let me explain it again. So green shaded region is my quantum field theory. So have in mind here you've got, QED or QCD or something in the green shaded region. So these are the spatial dimensions of the quantum field theory. And we're learning about that quantum field theory by just doing a gravity calculation in one dimension more. So I can't draw, 4 spatial dimensions. So I'm displaying a 2 spatial dimension quantum field theory being captured by 3 spatial dimension gravity. Okay. Now, I decide that I want to calculate the entanglement entropy in that quantum field theory. So again, to set up my definition, I split my spatial region into 2. I call this A, I call this B. Trace out degrees of freedom in B. So what Ryu and Takanagi propose is that the entanglement entropy is calculated by finding a surface in the bulk which ends on A and is, in mathematical terms, homologous to A, and it should be minimal. Right? So it should extremize the error. And then the entanglement entropy is basically the area of this surface divided by 4 times the Newton constant. Okay. So in the example I showed here, so we have a 2 plus 1 dimensional quantum field theory. So 2 spatial dimensions of the quantum field theory, 1 time dimension. The boundary of my entangling region is hence a line. What I'm instructed to do is take my 4-dimensional bulk, so my 4-dimensional gravitational space, and find a 2-dimensional surface which basically ends on this. And the way I choose that surface is that it should have, it should extremize the area. So it should have the smallest area of all the surfaces which ends on A. That's my prescription.
It's like a soap bubble on this. Right?
Exactly, it's exactly a soap bubble. It's exactly the same equation. Okay. So that's, this is a very simple prescription for calculating. So in particular, the most famous example of holography is the relationship between, say, anti-de Sitter and supersymmetric Yang-Mills. And this prescription allows you to compute the entanglement entropy in supersymmetric Yang-Mills theory. And I just told you a few minutes ago that calculating this in gauge theories is tremendously problematic, but this gives you a prescription not only to calculate it in a gauge theory, but to calculate it in a pretty complicated gauge theory, right? Because it's supersymmetric Yang-Mills. Now, I'm not going to explain in too much detail where the formula comes from, but I do want to sketch a little bit why you might believe this formula. So this is one of the few calculations I want to do with anti-de Sitter. Okay, so we can write the metric for anti-de Sitter. So we've got a radial coordinate, we've got a time coordinate, and we've got 2 spatial coordinates, x and y. Okay, and now the radial coordinate is, the one that's extending down in this direction. And the quantum field theory lives in a background which is just 3-dimensional Minkowski space. So it's got time and then 2 spatial coordinates, x and y. So if you just write down the soap bubble equations in this background for a 2-dimensional surface which ends on a region, and you just, calculate the area of that soap bubble, you find that the area of the soap bubble behaves as the length of this boundary divided by epsilon to a power, where we had to, so the boundary of the space-time is at rho equals 0, and we said that going to the boundary of the space-time is like probing the UV physics, the ultraviolet physics of the quantum field theory, so we have to cut this off. So we get exactly the same cutoff as before, and we will also get, where appropriate, logarithmic terms shown as well. So when they wrote down this formula in 2006, one of the main pieces of evidence that they gave that their formula was actually correct was the fact that when they plug in, when they work out the area of these surfaces in anti-de Sitter matrix, they get exactly the structure of the entanglement entropy, which is known to be the case for conformal field theory. And they explored this in conformal field theories in a variety of dimensions. They explored, in a sense, more complicated cases as well to justify the formula. Okay.
very evocative of Wilson loop evaluation.
I'm going to briefly mention that in just a moment. So can I just say very, very briefly that actually, I will say it now, that actually in holography, if you wanted to evaluate a Wilson loop in the quantum field theory, you would do a virtually identical calculation holographically. So you would actually evaluate really a minimal surface. The only subtlety here is that the Wilson loops also probe, it might be anti-precipitant spheres, and the Wilson loop is very sensitive to what happened in the sphere part, but it's a very closely related calculation.
And can you draw a map with the string tension and the additional term coming from the expansion of the Wilson loop? As indeed you're talking about the area of the surface.
Yes.
And so it's very evocative of the final picture described by the Wilson loop.
That's right. In the Wilson loop, that's very well understood. Yeah, in the entanglement entropy, that's not so well understood. So the Wilson loop is already in Mollisen's paper in 97, 98. That's yeah. Okay. So, so a basic question which many of us, including me, had in their mind for many, many years was, why should the entanglement entropy be calculated by a minimal surface? So, are there observables in holography, like correlation functions, that were kind of quite sort of sharp arguments for the recipes which were given in 97, 98 for how you could calculate it? Whereas here, this recipe sort of came out of nowhere, and the justification was that when you kind of plugged in the recipe, that it really reproduced the expected physics of entanglement entropy. Okay. Now, in recent times, people have understood why it is computed by minimal surfaces. And I will very briefly explain this. It's a bit of a subtle argument, so I wouldn't worry for the rest of the talk if you don't follow this argument. But just to say that there is an understanding now of where it comes from. So this relies on this thing called the replica trick, which is basically this rewriting of the entanglement entropy that we did before in terms of the limit as n goes to 1 of trace rho to the n. Okay. So this trace rho to the n, this Renier entropy, you can do yet another just very simple manipulation of rewriting of this in the following form. So we write the entanglement entropy in terms of the usual partition function. So Z1 is just the usual partition function of the quantum field theory. So that partition function obviously has no information about the shape of the entanglement region or anything. And then the information about the shape of the entanglement region comes from this part. So this thing here is Zn. So what is it? So it's a partition function, and now the partition function is not on a flat Minkowski, of quantum field theory on a flat Minkowski background. It's a partition function on a weird space, which is called a replica space, which is basically copies of Minkowski space joined together. Okay, so before I go back to the expression, let me explain what I mean. So here's the calculation we want to do. We've got, again, a two spatial dimension of quantum field theory. Time is in the third direction. Here I've made it Euclidean just for convenience and calculations. Here's my shaded region. I want to calculate the entanglement entropy associated with that shaded region. Okay, so this term of the expression is just the partition function of my theory. Actually, I should have carried along, just some toy, whatever partition function of whatever theory you have in mind. You just calculate the partition function in the usual way in the space. Now, Zn is the following. When n is an integer, what you do is you basically take n copies of this space and you join them together. And you basically join them together by taking, instead of taking this circle to have periodicity 2 pi as you go around this, you take it to go around n times, and you put them together. So if you take a sort of slice, a vertical slice through this, you do one copy, you do a second copy, and you do a third copy. And of course, when you start gluing things together, there are conical singularities where you glue things together. So the replica space, this is an n equals 3 replica space. It's 3 copies joined together, and there's a conical singularity at the origin of this tau circle, basically at the boundary of the entanglement region. So the replica space knows about the shape of the entanglement region. But now what we're asked to do in this expression is to calculate the partition function on this replica space. So I do my quantum field theory on this pretty weird background, and I calculate the partition function on that background. And then I plug into this expression and I take the limit n goes to 1. And you might worry about the analyticity as n goes to 1 because, you know, surely it looked like n was an integer, but it turns out that that's not really an issue for the discussion we're having here. Okay. So now let's see what this has to do with where the Ryu-Tachyanagi formula comes from. Okay, so I told you in holography we can calculate the partition function. So if you want to remember only one thing from this talk, this is probably a good thing to remember about holography. So the partition function of a quantum field theory in holography is calculated by basically just taking the Einstein-Hilbert action, and usually what we do, you know, so you go to a GR course, you take the Einstein-Hilbert action and you derive the field equations, and then you solve the field equations, and you look at the solutions of the field equation. What we're instructed to do in holography is take our solution of the field equation, so here for me it might be anti-de Sitter space, and plug this back into here and calculate the value of that action on shell. So I just substitute my solution in the equations of motion, put it back in here, and I get the on-shell gravity action. And that is computing for me the partition function of the dual quantum field theory. So calculate the gravity action for anti-de Sitter, that tells you about the partition functions for quantum field theories. Okay, so that's the defining holographic relation. Now, as I showed on the previous slide, these replica spaces, they've got conical singularities in them. So your original space, whatever original space you were doing holography on, it has some Ricci scalar curvature, but the replica space, in addition to that curvature, it has certain contributions to the curvature associated with the conical singularity. So it's got some extra contributions to the curvature. And in this expression, there will be a cancellation between the terms coming from the replica space and the terms coming from n copies of the original space. So all these bits where they've got the same terms will cancel, but the contributions that come from that conical singularity don't cancel. So all the terms cancel in the expression, apart from the ones which come from the conical singularity, which is the surface. And when they cancel, that's the thing that gives you the area. Okay. Now again, if you don't follow the details of the derivation, it doesn't matter for what follows. I'm just arguing this to say there is now a nice derivation. And in particular, that means that if you want to do a more complicated version of holography, where instead of using the Einstein-Hilbert action, you have higher derivative terms, or you have matter which is coupled to curvature, you can actually derive an analog of this expression. It's not quite the same, but you can derive an analog of this expression. So it's now a systematic derivation. Okay.
Does the cosmological constant matter?
No, because again, that's going, all the contributions between the replica and the n copies of the original space, everything cancels except the terms from conical singular. So it works kind of pretty elegantly. Okay, so in a sense, this whole kind of replica picture, this is sort of explains why the boundary of the entangling region plays such a special role. That was what kind of controlled the entanglement entropy. And it also explains when you continue that into the bulk in a minimal surface, why that plays the roles of the entanglement entropy. Okay, so that's a nice derivation. I should say that derivation I've just given you is due partly to Modest Senna and also partly to sort of refined by myself and my student William Woodhead. Okay, now, so we now believe that this expression is calculating for us the entanglement entropy, right? And so the next question is, well, what are we actually going to do with it? Okay, so how are we gonna use this in quantum field theory and condensed matter theory? Okay, so we have a very simple prescription for calculating the entanglement entropy in theories that you can describe holographically. So holographically, the type of gauge theories that you can describe with gravity of one higher dimension The ones that we know how to do now are generally very strongly coupled theories, and should be large n. So we're talking like, say, SUN theories where n is large. N is probably not 3 or 4, right? We have to take it larger. But in that class of theories, we've got a really simple prescription for calculating the entanglement entropy. And as I said before, we also have in holographic models of spontaneous symmetry breaking, explicit symmetry breaking. We have things which are basically superfluids, so you can also calculate entanglement entropy for superfluids. And so there's an enormous amount of interest over the last 10 years of, just basically, okay, I guess this is partly what theorists do, is just to kind of go and explore it in all the cases you can, right? So take all the models and calculate entanglement entropy, see what happens. Okay. And as I said before, small regions in the quantum field theory. So if you're looking at very small scales in the quantum field theory, so small entangling regions, that's going to be sensitive to UV physics, and it's not going to involve surfaces going very deep into the interior. Much larger regions are very sensitive to what happens at large scales, infrared physics in the quantum field theory, and they're much more sensitive to what happens in the deep interior of the space-time. So if you're interested in what is the infrared behavior of a quantum field theory, entanglement entropy is a pretty good measure of that behavior. So this was pointed out, I think, in papers by Lisa Halscher and Subir Sachdev. That's from the condensed matter side. These are condensed matter people who are interested in holography and ADS-CFT, and pointed out by Igor Klebanov from the particle physics type of side. So you can kind of take this statement two ways. So if you're trying to do holographic engineering, you're trying to engineer a better model for modeling QCD. So you know what kind of physics you want to have in the infrared. Engineering the space so that the entanglement entropy has the right features. Basically, you can engineer the inside of the space so the entanglement entropy has the right features that you expect for the theory that you're actually interested in. And conversely, if I give you some holographic background and I calculate the entanglement entropy by doing minimal surfaces, that will diagnose whether the infrared of that theory, whether it's a confining theory, what's going on in the infrared. And they pointed this out. Now, picking up on the comment earlier, you would say, well, actually, you want to diagnose confinement, don't you use Wilson loop, Polyakov loops, etc. And absolutely you would be right. And in fact, the fascinating thing is that the calculation is almost identical for Wilson loops and Polyakov loops, because holographically, they also involve minimal surfaces. So why were people so keen on doing the entanglement entropy? I think it was because it's the new game in town. It's a very interesting question as to what new you learn from doing entanglement entropy as opposed to the more traditional measures of, say, confinement, such as Wilson loops and so on. But certainly there's been a lot of interest in doing it. Okay. Now I want to sort of talk a little bit about, what we learned about conformal field theories from doing this. So I said before that if you've got a conformal field theory, you typically, as well as these terms which involve powers of the UV cutoff, you also have things which depended logarithmically on the width of the entangling region. So there were always terms like this expressions. And more precisely, these show up for conformal field theories in 2, 4, 6, 8 dimensions, so even dimensions. So this term in 2 dimensions is very famous. So the A, I call it A for sort of generic dimensions, but specifically in 2 dimensions, the A is really proportional to the famous C, the central charge of the 2-dimensional CFT. So it's related to the trace anomaly of the CFT when you put it on a curved background. And there's a very famous theorem due to Zamolodchikov from 30 years ago that in a 2-dimensional theory, the C function decreases monotonically along an RG flow, and it's stationary at the fixed points. Okay. So, another reason to be interested in entanglement entropy is because we see in the case of 2 dimensions, so of course 2-dimensional CFTs, pretty much, I think we know almost everything we could possibly want to know about them. But we see that the C quantity that we know is related to the semological C theorem shows up in the entanglement entropy. And I could spend, an hour or so explaining exactly why it shows up here, but it certainly, it shows up there. So in odd dimensional CFTs, actually I should say, okay, the C theorem is in 2 dimensions. In even dimensions, there is a lot of work on trying to prove analogous theorems. So there's a long-standing discussion of trying to relate the trace anomalies in 4 dimensions to theorems analogous to Zomologikov to show that there's, the coefficients are stationary at fixed points, to show that there's a function which decreases monotonically along an RG flow. And there's sort of an almost proof in 4 dimensions with some gaps in it. 6 dimensions is kind of harder. But, there's certainly, candidates for generalizations of the C theorems in even dimensions.
Is this then what they call the A theorem?
The A theorem, exactly. And that's why I use the coefficient A.
Just because you keep reading.
That's right. So there's almost proofs of this. Okay, but it's a very long-standing puzzle for what you would do in an odd dimensional conformal field theory. So if you're in 3 dimensions, 5 dimensions, and so on. So you might say you don't care about exotic dimensions like 5 and 7, but 3-dimensional CFTs are certainly interesting for, abstract purposes, but also 3-dimensional CFTs are probably relevant to some quantum critical points in condensed matter. They might be relevant to high temperature superconductors, for example. So there's some reasons why you might care about this. So in odd dimensions, the trace of the stress tensor cannot pick up a term like I wrote here, just on dimensional grounds, because the curvatures are even dimensional, and this is an odd dimensional operator. So there's you can't generate a trace anomaly. And so there's a very long-standing puzzle of what quantity would you actually use to measure the degrees of decrease in degrees of freedom along an RG flow. Okay, let me go back to here. So we decided that in even dimensions, the entanglement entropy, the A quantity, which is related to the trace of the stress tensor, shows up in entanglement entropy. So it's a natural suspicion to sort of look at what happens in odd dimensions and see whether there's a term in the entanglement entropy that somehow is measuring the numbers of degrees of freedom. Okay. So what quantity could we do that measures this? So, as I said, this is a long-standing puzzle, and over the last few years there have been a few speculations about this. So, the best candidate people have had is in a 3-dimensional conformal field theory, is to put the theory, 3-dimensional conformal field theory, to put it on a 3-sphere. So that means you've got to, wick rotate and put it on a 3-sphere, and then basically calculate the log of the partition function on the 3-sphere. Now the F theorem in this case would say that this quantity, F, which is basically the log of the partition function, it's strictly positive, and it's stationary at any fixed point, positive in a unitary conformal field theory, and it decreases as you go along the RG flow. So as you go along the RG flow from the ultraviolet to the infrared, F would actually decrease. And this was a proposal made by the Princeton group in about 2010, Jeferes, Plymouth, Pufu, Safdie. So they had various reasons for believing that this came true from supersymmetric examples. They had a kind of, some large number of examples where they can actually check this explicitly, and this was what prompted them to make this conjecture. And this was, it doesn't look such an unreasonable conjecture, because we could reformulate the A quantity in terms of a particular variation of the partition function in even dimensions. So this, it seemed a not unreasonable conjecture. Okay. So I think I'm going to skip the explanation of the next point. But this sphere partition function is indeed very deeply related to the entanglement entropy we've just been discussing. So in particular, that sphere partition function, so put the theory on a 3-sphere and calculate the partition function, you get the same answer as you get for calculating the entanglement entropy of a disk entangling region in flat space. So it's basically the same quantity. I will leave the explanation for, you know, if people want to see the slides afterwards, but just sort of leave the statement. So this sphere partition function here is exactly the same as what we get for the entanglement entropy for a disk region in three-dimensional theory. But this brings back the puzzle that I had in the first part of the talk, because the A anomaly coefficient is something which is finite. So, you know, this is something, you know, which we discuss, you know, if we teach a course on conformal field theory, we discuss where that comes from. It's just a perfectly finite coefficient. It doesn't have any scheme dependence. But the partition function, again, without thinking about how you're going to put a CFT on, you know, all the details of it, you know that when you calculate a partition function, it's a UV divergent quantity. And I've already told you that the entanglement entropy is a UV divergent quantity. So implicitly, for this conjecture to make sense at all, I really have to mean that the F quantity is the partition function on the S3, but it's a renormalised partition function. Okay. And then you could say, well, but what about scheme dependence? So do I get the same answer if I use, you know, dimensional regularization or zeta function regularization? Are there any finite terms? You know, is there any possible scheme dependence? And this was not something which had been discussed in the literature, so people had, in a sense, implicitly dealt with this, because I told you, you know, people tried to check this F conjecture in a number of cases. So they would take their favourite supersymmetric quantum field theory and they would calculate the F, and they would implicitly choose a scheme, but they wouldn't explicitly state what they had done. And they would calculate this sort of holographically, and again, they'd implicitly do something, but they wouldn't explicitly say what they'd done. Okay, so what I showed you my student William Woodhead last year is two things. Firstly, that F is indeed renormalization scheme independence, so you can't actually write down any finite counterterms. And secondly, that, you know, we said that this F, the sphere partition function and the entanglement entropy are, you know, basically they're related to each other. Well, it turns out that the entanglement entropy can itself be renormalized. So we don't need to use, if we're quantum field theorists, we don't need to use this kind of rather clumsy quantity which involves a regulator and a cutoff. We can actually sensibly define a renormalized entanglement entropy. Okay. So I'm going to explain both of these in the remaining sort of few minutes. So this proof is, you know, to actually fully prove it is a little bit complicated, so I'm just going to, you know, sketch where it comes from. So when you calculate F holographically, so we want to calculate the partition function of a theory on a 3-sphere, which can be calculated by 4-dimensional gravity. I told you to calculate the partition function for your quantum field theory. You basically just calculate the on-shell value of the Einstein Hilbert action. Now my cosmological constant, I just fixed to a specific value 6. Okay, so I calculate the on-shell value of the Einstein Hilbert action. But actually this space is a non-compact space, and, you know, the partition function I told you was, you know, divergent. And so, you know, to get a finite answer for that, you clearly have to renormalize. And about 15, 16 years ago, Sebastien and others systematically showed us how to do that. So if you want to calculate the renormalized bulk action of ADS4, which calculates for you the partition function of a CFT, you use the Einstein Hilbert action, and then you add certain boundary terms to it. Okay. And what we showed is that there are no possible finite counterterms. So these terms are all basically contribute to terms which behave as powers of this cutoff epsilon. There's no possible finite counterterms that can actually show up in this case. So if you calculate the renormalized action of ADS4 with S3 slicing, so you calculate the partition function for any CFT on S3, which can be described holographically, it's basically given just in terms of inversely in terms of the Newton constant. So the F quantity is basically up to factors of pi over 2. It's basically inversely related to the Newton constant. Okay, and again, there's no possible counterterms that can do that. So essentially what this is telling you, so remember F was meant to be counting the number of degrees of freedom in the quantum field theory. This is telling you that the number of degrees of the freedom in the quantum field theory, conformal field theory, are inversely related to the Newton constant. So if the Newton constant here is large or small, as it, if this is small, this tells you that you have a very large number of degrees of freedom in the conformal field theory. This was my statement before that when gravity is a good description, we're always getting theories which have a large number of degrees of freedom. So this is indeed capturing the physics that you expect. Now, the entanglement entropy should give us, entanglement entropy for a disk should give us precisely this expression. How are we going to get something which is finite and renormalized? Well, actually, we just go back to this defining expression for the entanglement entropy in terms of the partition functions. And we realize that instead of just using these bare regulated partition functions, we can just renormalize with any renormalization scheme we want. And this seems a remarkably obvious statement, but it seems nobody had realized this before us. Okay, so you just use the renormalized partition functions, and again, you can kind of do some kind of careful proof to show that in the case of the disk, there's no dependence on which renormalization scheme you actually use. Okay, so actually, there's an intuitive physical picture. So here's our Ryu Takanagi surface, which is actually calculating for us the entanglement entropy. And so we calculate the area of this surface, and essentially what we're instructed to do is just to renormalize the area of that surface. And people had done this in holography before. They talked about renormalized minimal surfaces. So this is a paper from the late 90s. Witten had talked about it, and Gross talked about it in the context of Wilson loop. So Wilson loop is also computed by minimal surfaces. Gross talked about doing that. Okay. And so if you actually calculate the renormalized entanglement entropy, you've got that term. That was the area of the surface. That's your soap bubble functional. And then there's a term which basically just subtracts the length of the boundary and renormalizes this. It renormalizes the area. And again, you can show there's no possible finite competence. So you plug it all in, and you get exactly the same expression as before. It's got the right relation. So the renormalized entanglement entropy of the disk is minus the F quantity. So positivity of F is negativity of S. So that works really kind of nicely. Okay. So that's a sort of nice result. Now let me sort of just briefly explain what happens under RG flow. So we've demonstrated a nice definition of F. We've demonstrated that it doesn't depend on what scheme we use. We demonstrated that the entanglement entropy can be renormalized. But to really get an F theorem, you need to ask what happens under an RG flow. So you take your CFT and you deform it. And the claim is that the F quantity should decrease. So if you flow from the ultraviolet, F should actually decrease, and correspondingly the entanglement entropy should strictly increase. Okay. Now, there's a lot of examples in the cases that, I said people just went through a bunch of examples. So a lot of people showed that the infrared F, if there's an infrared fixed point, was less than the F for the ultraviolet fixed points. There was very little evidence for the monotonic decrease of F. Okay. And what we found in certain examples that we had, so this is cases where we can describe an RG flow with a gravity solution. We found, in fact, that F does not decrease under the RG flow. So we've got cases where, this is a case where F decreases under the RG flow. So this line describes for us the dimension of the operator that's doing the deformation. So operate in the range where delta is between 3/2 and 5/2, that's a relevant operator still, the F quantity actually increases as you go along the RG flow. And then something special happens at 5/2, there's scheme dependence. Okay, so what this means is that although it's true in all our examples that the F at the infrared conformal field theory is less than the F in UV quantum field theory, the F doesn't actually decrease along the RG flow. We have an analytic argument about why this happens too. So either the flows are unphysical for some reason, so you always have to be careful in these A theorems, C theorems and so on, that you kind of satisfy the small print, is it unitary? We think so. is there some small print that we have evaded? So either they're unphysical, or F doesn't decrease monotonically. And we think actually that we haven't found the hole for why these are unphysical. So we think that this conjecture that the log of the partition function on S3 is the analog of Zamenhof C quantity is not quite correct, because we have examples in which this is not true. Okay, so because F is basically the same as this renormalized entanglement entropy, that's also not changing monotonically. But there is something which is changing monotonically. So if you take a disk region of radius r and take two derivatives of it, that's something which is monotonic. And that's related to this additivity property of entanglement entropy I mentioned at the very beginning. So that sort of suggests that maybe the F quantity wasn't the best measure of the degrees of freedom. Maybe we really should be looking at the entanglement entropy and just taking derivatives of it. Maybe that's the best quantity to be looking at. Okay, so let me summarize. Entanglement entropy can be computed holographically in strongly coupled gauge theories. In quantum field theory as a whole, entanglement entropy can be renormalized. So if you're a condensed matter physicist, you may be happy to be working with this regulated quantity because you have a lattice cutoff in your system, a real physical cutoff. As quantum field theorist, I'm personally very unhappy with working with a quantity that's regulated. I would rather work with a quantity that's renormalized. Now we give you a definition so you can renormalize the entanglement entropy. And you can also, I should say, get some intuition about what this means in terms of the number of degrees of freedom needed to purify the system. We can go back to those concepts. Gradients of the renormalized entanglement entropy seem to be the best option to capture the reduction in degrees of freedom along the RG flow. Just the partition function doesn't seem to quite get the right picture. So what has come out of the holographic discussion is, I think, a lot of progress on understanding entanglement entropy in quantum field theory over the last 10 years. Extending that to quantum gravity is still very hard. Lots of papers come out about that. I haven't said anything about that, but people are trying to do it. But I think there are two kind of very sort of key questions. One is, people got into calculating the entanglement entropy because of sort of condensed matter motivations. And then there was a sort of a nice prescription in holography, and they said, well, let's calculate it. But we haven't actually come up with a sort of reason, a good reason or a good understanding of why we should calculate this, as high energy physicists. So I said it's a very nice quantity for this discussion of renormalization group flows. But it's sort of, I think, a very big open question. Is there another reason why we would actually want to calculate entanglement entropy in a quantum field theory for other purposes? Would it capture something that Wilson loops, Polyakov loops wouldn't actually get? And is it something which would be computable in lattice physics? Again, certainly condensed matter physicists effectively do calculate it on the lattice. They for sure calculate it on the lattice, and then they kind of often compare it to analytic calculations in the limit that their spin systems, that their lattice systems, get interoperability. But is it something that we should, as particle physicists, be interested in? And the other big question I'm not going to go into here is, can you get a workable definition of entanglement entropy in quantum gravity? And why would you want to do that? This is because of the long-standing question about black hole physics. So the black hole puzzle can be basically phrased in terms of entanglement entropy. It would be saying that we actually expect when a black hole evaporates, we should eventually find out how it was formed if the entanglement entropy at late times actually goes back to zero. So a pure state has entanglement entropy 0. So if a black hole evaporates and we eventually find out how it was formed, the entanglement entropy as we go to late times should decrease back to 0. But for that to even be a sensible statement, we would actually have to write down a more rigorous definition of entanglement entropy in quantum gravity along the lines of what I've been doing here. It's clearly not a meaningful statement unless you can actually really define entanglement entropy. Okay, so I'll stop there. Apologies for running over a little bit. Thank you.
Questions? Antonio?
I have
So maybe some of them will be discussed later. So the first one is really a curiosity. I'm a lattice person, shame on me. Entanglement entropy has been already measured for various gauge theories. Why you ask if it is computable on the lattice? Don't you like the way in which it has been measured?
Okay, so why would I like to you mean measures?
Yeah, I can name a couple of people that published paper on measuring for SU2, for example. Etsuko Ito, or I think also the Turing group measured it.
You mean measured as in a
As
laboratory?
made no, on the lattice.
Measured on the lattice.
By making simulations on
right.
computer.
So why would I be interested in doing this on the lattice? I should refine it. I would be interested in certain theories, to do it in certain theories. So we have theories where we know the answer from strong coupling, and we would like to know how it changes at weak coupling. So, you know, an example of this would be the kind of theories that Masanori Hanada is interested in. So supersymmetric theories, where there's non-trivial change between the weak coupling and strong coupling result. We would like to understand the weak coupling result because of the relation to black hole formation. So, in that sense, it would be interesting. And one of the things I would like to understand how to do I would like to explore on the lattice is exploring the meaning of the renormalised quantity. Yeah, the renormalised quantity is in a sense new. I mean, the physics underlying the renormalised quantity is new, and I have again strong coupling examples of, say, symmetry breaking, where generically the same thing seems to happen in the entanglement entropy. But I would like to see, you know, this repeated on a lattice to actually see in different regimes of the coupling, to understand whether this is strong coupling effects or whether it's due to, you know, particular symmetry breaking effects. So I think it's a fair statement. It's not. Is it, you know, the question is not is it computable on the lattice? Is it computable on the lattice? In the case of the theories that I'm interested in. Yes.
So if I can just jump in, it seems that I can see two issues. So one is it seems that you want to do the continuum limit, which I guess, so the epsilon going to 0.
That's right.
But not the infinite volume limit necessarily, because you've still got these finite L.
Yes.
So
the way which is done
so
is exactly that. It's done in a finite. It's done in a fixed box.
Yeah,
indeed.
Yes.
okay,
And
fixed
there
box.
is exactly measured out of difference of free energy of two different sides fixed boxes.
And of course, another issue is you have this definition, the F theorem and stuff. You had this definition on a three sphere, which of course is a geometry that would be different from
And that's
where
at the moment
where you have a
unachievable
three
and is
tones.
another
That's
story.
right. That's right. But that's not necessary. I mean, for computing my entanglement entropy, he doesn't need to be on peculiar vacuum project. Doesn't have the theory
Again,
cube.
just to
Yeah.
understand it better, I mean, the theory you are referring to are very often useful for constructing BSM theories. Are you trying to think about those? I mean, these where you can disentangle or detach the behavior in infrared from one of the arrival are clearly not QCD-like if you want.
I think I have in a sense a bigger worry, you know, a bigger concern, which is we have, I mean, analytically we have very few examples of, you know, weak coupling calculations of non-trivial symmetry breaking, right? By definition, now you're not going to get this. We see certain generic patterns of behavior of the entanglement entropy in the strong coupling examples. But is this strong coupling physics or is this symmetry breaking physics? Yeah. So it's not specifically that I want it to be BSM physics. I simply want to know what is the signal of strong coupling and what is the signal of particular types of symmetry breaking and so on. There's more specific questions as well. Like, you know, we have particular predictions of how things should behave as you change the coupling, and, you know, okay, the lattice could obviously verify them. That would be nice to do, but, you know, that's a nice check, right? The bigger thing is just to understand what is strong coupling and what is symmetry breaking. So.
Any other question?
Simple question, at least conceptually, I think. So, does one know if I calculate, say, taking ADS CFT and ADS QCD, so if I compare the conformal with the confining situation, how would the entanglement entropy change?
Right. So we understand. So we understand how this happens. I mean, so in the case of confining, I mean simply the scaling changes. In a sense, it saturates. So as you start increasing the entanglement, the scale of the entanglement surface, the entanglement entropy after a certain sort of scale, size of the entanglement region, it just saturates and it doesn't change anymore. I think that's a sort of physical intuition, and that in a sense the critical size at which it starts to saturate is related to the confining scale. So that's a sort of generic physics. I think that's not specific to the holographic models either. I mean, that generic behavior you can see is going to happen. And again, you can kind of, there are various ways to think about it. And I mean, a simple way to think about it is in terms of, thinking about what is the dominant correlations in the entanglement, in the entanglement entropy, and how that will be controlled by the effective correlation functions in particles of different scale.
So that seems consistent with his ADS QCD picture of confinement. If your entangling surface is getting larger, you're probing deeper into the bulk as a cutoff. So
That's right.
Yeah.
I should say ADS QCD with a kind of cutoff. I think we'll never get all of the right physics right because it's too ad hoc. The examples I referred to here are not ADS QCD, but they're top-down sort of supersymmetric models which have confinement, but they're at least nice consistent quantum field theories. And in the interior, you typically don't have a hard wall cutoff. You just have some sort of nicer behavior. Yeah, but still the same physics is there. There's basically some sort of wall in the interior, effectively, which stops your surface going too far. That's the intuition.
Anyone else? Anything else? If not, it's nice to speak again.